Good. All right. So let's continue here. We said we want to do some intersection tests of objects. So and here often, or we want to do intersection tests, and most importantly, intersections between lines and objects. Here in the slides, I very often wrote rays and object because, like I said, in ray tracing, these intersection tests are very important. But also, in general, we can calculate this in general as a line. A ray is basically the same as a line. It's just something that we usually use as a phrase when we want to describe something where we start from a very specific position and then only go in one direction. So we're shooting the ray in one direction, or we're looking in one direction. And then, of course, so if we have the observer here with our eye, then we are looking in this direction. And then, of course, if we have specified this as a line, we could say we put our support vector here. That means we get this value for t equals 0. And then we have our direction vector here. That means in this direction we have all the values for t larger than 0. And here we have it t smaller than 0, or if we're only interested in array, only interested in what happens in front of us, then of course we can ignore the part behind it. And that's why I'm interchangeably using array and lines in the following now, so don't be confused about this. Good. And the calculation is actually pretty simple and a good illustration about why these different representations of objects are quite handy, because if we, for example, want to calculate the intersection of a line with a plane, then if we have the line in parametric representation and the plane in its implicit representation, it's just some very simple basic arithmetics that we have to do. In fact, namely, we take the plane, the line, or the condition that we have, of course, for all the intersection points of the plane and the line is that they must fulfill both equations. They must fulfill the equation of the line and they must fulfill the equation of the point. And they must fulfill the equation of the plane and they must fulfill the equation of the line. And if we take the line in parametric form, we can use that to calculate the points, and then we can verify it with the implicit equation if they are on this plane. So we can take the points that we calculate with the line and just put them into this parameter. So n and p0 are the constant values that define our plane. P is the variable value that represents the points that are on the plane that we can verify. So if we put the lines from all points from the line into that equation, if it equals 0, then we have the points that are on the plane and on the line, so our intersection points. So if we put that in here, we get this equation, and we see here the only parameter that we have is t. So we have an equation with one parameter, and that can be solved by just solving for this parameter. So we just do some arithmetic transformations, and I think you will have a lot of them or some of them in the tutorials. And that way we can then calculate the value t. We get a value t, I don't know, t1. And this t1 is then exactly the value of this intersection point of t1. Now there is, of course, the possibility that there is no solution to this, which would mean the line is parallel to the plane, because then there is no intersection point. It could also mean that there is an infinite amount of solutions, which would mean the line is on the plane, because then also the amount of solutions is, of course, all the points on the line, which is an infinite amount of solutions. And the same approach we can use to calculate the intersection of a ray and a sphere. And again, we take the ray in its parametric representation here, and then we put this here in the equation of the sphere, where we have the x and the y and the z value. Now if we put that in, we get this here, which looks a little complicated, but it's just simple, put it in, arithmetic transformation. But the difference to the line and the plane is to line and the plane case is, of course, that we have here something to the power of 2. So we don't have a linear equation, but we have a quadratic equation. And I hope that from school you know how to solve quadratic equations. If not, I'm not covering it here because it would really be too boring for a lot of, for the majority of people who I assume would already know this. But there is a chapter about this in the book, so you can look it up there. We solve a quadratic equation by using, we can solve a quadratic equation by using this formula here. So we take this equation here, which is the intersection of the line and the sphere, transform it in a way that we only have t's here, t to the power of 2 plus something t to the power of 2, t and constant values. So these are all then the things here. We get the t to the power of 2, but we also get single t values, linear t values. And then if we combine them, we get these parameters here. And then we can just put them in the equation, and then we get a solution. In fact, we do not get a solution. We might even get two solutions because we have a square root here. And of course, the square root can be positive or negative. So we have two. This equation gives us two possible solutions. And from a geometric interpretation, this is also clear. You already see it at the right side of the image. If we calculate the intersection of a sphere with a line, we get, of course, two intersection points, one where this line enters the sphere and one where it exits the sphere. Of course, there is also the case that the line misses the sphere, or that the line just touches the sphere at one point but doesn't go through it. In that case, we can get only one solution, and in that case, we get no solution, which is exactly the case that I listed it here. If this value under the square root is negative, of course, this equation doesn't have a solution, so that is this geometric case here. If it equals 0, it only has one solution. So plus minus 0 is always the same. So we only have x and not x1 and x2. Oops. Which is this case here, that it touches the sphere. And of course, that is then the other case where we have two intersection points. Good. And then, of course, in relation to this ray intersection that I said, when we have our ray that we shoot from our eye or from our camera towards a scene, it can of course also happen that if we are inside of the sphere, that we get a positive and a negative solution, which means then from a geometric interpretation we are inside of the sphere and the other side of the ray is behind us. Good. Yeah, so we talked we talked about some basic simple shapes, planes, lines, and circles and spheres in 3D. But we didn't talk about yet triangles, which I said at the beginning are the most important geometric shapes probably in graphics, because we can model everything with triangles. They're hardware supported and they're basically everywhere. So we need to also talk about the triangles. And of course, we can very easily define a triangle by just specifying three vectors that point to the vertices of the triangle. But similar case as it is very easy to specify a line with 2 points, we need a way to calculate all those points that are on the triangle, and not only around the triangle, but also we need to know which points are inside of the triangle when we want to draw not just the edges of the triangle, but also the center of the triangle. So, and to do this with what we already learned, of course, we can say that all points are inside of the triangle if they are on a plane that is defined by the triangle in 3D. But of course, that's also true for all the points that are outside of the triangle in this particular plane. So the plane helps us in specifying these points, but it doesn't give us a solution. We need a way to specify if a point is on the plane inside the triangle or outside of the triangle. Now, to illustrate this, let's look at the 2D case first. So what we have is we have a triangle specified by the three vertices with vectors, and we have a point, and we want to know now if the point is inside the triangle or not. And we can describe this point, and if we have a Cartesian coordinate system, like a linear combination of the base vectors. So this is the part now where I said at the beginning I'm repeating a little bit of these coordinate systems later. So this is the repetition part. I already mentioned Cartesian coordinate system last time. Cartesian coordinate systems are what we intuitively always use in graphics or in general in geometry, are the coordinate system where you have a right angle and a similar unit at both sides. And if those base vectors are unit vectors, we even have then this orthonormal coordinate system, which is very intuitive and also very easy for the calculations, because then the base vectors have also a length of 1. And in fact, if we write it that way, then these actual Cartesian coordinates, which are the factors here, are basically what we intuitively always use as a vector when we talk about a vector. So we can define this here as, or we defined it as xy, or in this case lambda mu, but we can also write this then, of course, as a linear combination of the base vectors, or the other way around. We write it as a linear combination of the base vectors, and if we know that these are the base vectors and that they are from a Cartesian coordinate system, then we do not have to write them. We can just write down the coordinates, which is exactly the same as the n-tuple of the vector that we defined at the beginning. Good, but we also said with coordinate systems that they, if they have a right angle and if we have unit vectors, that's very convenient and it's very intuitive. But we also I also explained last time that we can also have any linear independent vectors and make a linear combination of them, and then we can describe all points in 2D as well. So if you remember it, I tried to intuitively explain this by saying, okay, if we have a line and if we have a grid, and it's clear we can go by going along the row and the column, we can access every cell in that grid. But also if we have a line and two lines that are not parallel to each other, we can still go along one line and along the other one and still address all points in a 2D space. We're just not going straight up, but a little shifted. And that is what is illustrated in this image here. So we can take any linear independent vectors. But that also means, and then we get, of course, this grid, which is not like this regular grid that we know, but a little shifted grid, but still very intuitive that we can address all points by this coordinate system. But of course, that also means we could, for example, choose the two vectors as a base of our coordinate system that are in line with the vector 2 of the vertices of the triangle. It also means that we can shift the origin to one of the vertices of the triangle, and this is exactly what is done with this so-called barycentric coordinate system. What we do here is we describe a point P by scalar multiple of the two base vectors, which are the vertices of the triangle that you see here, which is the difference of the points to the triangle. So it's similar to a plane, of course, because the 2D subspace of 3D is then, of course, a plane. And then, of course, we have to add this point A to it, because this is our new origin here. So we have the point A, and then scalar multiples of these base vectors, and then we can describe this vector P, can express it with respect to this coordinate system in the same way as before we expressed it with respect to the Cartesian coordinate system, which seems more intuitive. But of course, if you look at this, that you have a different, just a tilted or a parallel grid, with parallel cells, or cells that are parallelograms, it is not that much less intuitive than the other one, and it's also clear that you can address all points here in the 2D space. The advantage of this is the illustration of the x and y coordinates of this, or not x and y coordinates, b minus a and c minus a coordinates is actually more correct here. The reason why we're doing this is, of course, it helps us a lot in specifying if a point is inside the triangle or not. And to understand this, let's just look at this few extreme cases. If this is our point, or this is how we describe our point in this barycentric coordinate system, then we can, let's see what happens if we take beta and gamma 0. Of course, then we get this one vertex of the triangle. If we take beta 1 and gamma 0, then of course we get this vertex here. If we take beta 0 and gamma 1, we get the other vertex. So by setting 1 or 2 or 0, we can address all the vertices of the triangle. If both are 1, we can address the point that is directly on the opposite if we draw a triangle. So if we look at our grid here, this is this point here, which is not correctly drawn here, but you get the idea. So it's like a parallelogram where we address the opposite side of the cell. And if the points beta and gamma are within 0 and 1, of course, in this direction, we can go maximum till here. In this direction, we can go maximum till here. So it is clear that these are the points here that are all inside of this parallelogram. And this is already almost what we want, because we want to know when are they within the triangle. And if you think about it a little bit, also from the geometric interpretation, if you think about it, okay, if we go here to 1 and have 0, then we are still inside of the triangle. But as soon as we go up here a little bit in that direction, we have to go down in the other direction. And that leads you then very quickly to this obvious solution that if beta and gamma are larger than 0, and their sum is smaller than 1, then the point P is inside of the triangle. So we have a very simple way to verify if a point is inside the triangle or not if we represent it in this barycentric coordinate system. And this representation is actually quite simple and quite easy. And this is actually one of the examples where I improved the images because I realized that a lot of people had problems with this last year, although it is really quite simple. So I hope that the images are helping you a lot. And we will see later how this is, why this is very helpful and how this is used also. For example, one of the usages why we want to have all those points in between is, of course, if we want to put color on the triangles. And then, of course, it is nice to have a way where we can say, okay, if we have here a gamma value and this moves from 0 to 1, we just have to increase it from 0 to 1 and then we can draw the color on all these pixels here. And drawing colors is, of course, the nice transition to the rest of the of what I'm going to talk about today. So this basically concludes the basic mathematics part that we had, and now we're no, there's a lot more mathematics next week, but the terms where the basic part where we talk about the basic geometric shapes, and but this is now something that you will need for the practicals, which is why I will also talk a little bit about shading now and introduce a very simple shading model. It is actually also quite nice because it shows a little bit also the application of some of the mathematical background that we talked about, and hopefully it will already become much clearer why we need all this or what's the benefit of having all these different representations. So we talked about like how we can represent and describe simple geometric shapes, not more complex like we have here, but more about simpler ones, like lines, spheres, and triangles. And so we can do some simple modeling already. We will later talk about the projection. I will not do this now. The projection, then the step of taking these 3D models and how to calculate then the 2D representation on the screen of it. I will do this later because you don't need it for the practicals, because in practice, of course, when you implement it, you have an API that provides you with this function. It is very helpful for you to also know what is really going on when you call that function, but it is not essential to do the practicals, which is why I will address it afterwards, later in a lecture. But the shading is something, of course, that you need to know now, because the shading is how you put the light and the colors and the light and the stuff on the object, that they look more interesting than this simple grid model. Not as complex as here, but some very simple shading we will do in the course. So let's start with the shading by, again, repeating some of the mathematics, and now you will see why these normal vectors are so important. This is just a repetition of the definition of a normal vector or a surface normal, because we're dealing with 3D data now. So a surface normal, if we have a flat surface, it's clear it's a vector that is perpendicular to that surface. And I already said last time, if the surface is non-flat, then it is defined as a vector that is perpendicular to the tangent plane in that specific point. Of course, that is not always defined. So for example, if we have something like a cube, then of course the normal vectors on these flat sides, these sides are flat surfaces, that is uniquely defined. But what is here at this vertex here, it is not clear. We can draw it like this, we could draw it like this, we could draw it in between. It is not uniquely defined because this point belongs to both sides, so it's not uniquely defined what is a vector that is perpendicular to this point. So when we implement that, we just need to make an exception here, but from a pure mathematics, this is something that is not defined. Good. How to calculate these vectors, how these vectors are really defined in a strict mathematical way. I will not talk about this in detail. If you're interested, I think there is a short chapter about this in the book, but that would go too far, and fortunately we don't need it because we have these representations where we can very easily calculate the normal vectors. And one of them is, of course, the implicit representation of a plane. And yeah, I really don't have to go into details here because that should be clear. If you have the implicit representation of a plane, you can just read the normal vector from it. And that is, of course, one of the advantages of the implicit representation. If you represent your planes in that way, you save the step of calculating the normal vector because you already have calculated it when you created the plane. With the parametric equation, it's not, you cannot directly read it from the equation, but you can also very simply calculate it based on the parametric representation because we just take the scalar, the cross product of the two vectors that are on the surface and then these two direction vectors, and then of course we see that this is a vector that is perpendicular to each of these two vectors, which means it's also perpendicular to the whole plane. So this is a normal vector to the plane. Of course, we have to be careful when we do light calculations that it could also be this vector here, and that depends, of course, in which order we do this cross product, because if we do it the other way around, we get the vector pointing in the other direction, and that is, of course, very important when we do light calculations. And that's the same for the sphere, where it is also pretty straightforward and obvious where we get the normal vector, because the normal vector is a vector that is perpendicular to the tangent plane at a specific point, but that is exactly the vector that points from the point P on the surface to the center of the circle, and that is something we can easily calculate. The difficult thing here, or the thing we have to be really careful about, is does it point in this direction or does it point in that direction? So if we are, for example, here outside and we do the wrong calculation, then for the light calculation later where we use the normal vector, our object will still be dark because the light is considered to be inside of the sphere. Of course, if we are inside of the sphere, then we really want to have this vector here. So we have to be careful which of the two vectors we take. Good. Yeah, so I already said that we need these normal vectors to do the light calculation. So in general, if we look at if we want to do light calculation, we need to have a little look into the physics of lights, how light behaves, how we humans perceive light, how it is reflected from object. So and of course for a simple shading model, we just use a very simplified view of that. So intuitively, of course, we can say that the way how we see an object depends on the actual object, on the material, on the surface, on the color of the object. But it also depends on the impacting light. If we have a light, a yellow light or white light, that of course reflects differently. If we have a very bright light or a very dim light, that reflects differently. But it also depends on where the observer is placed. So if I'm standing at a different position, or if I move around, of course the color, the light that the color that I perceive when looking at an object might change depending on from which side I look onto it, even if I look at the very same spot, because the position of me with respect to the object and the light has an influence. So to describe this, to model this, we need to model the characteristics of the light and our surface. We need to consider the distance of the observer and the distance of the light. And we need to consider, of course, the direction at which the light falls into this object or this specific point, and the direction at which I'm looking at it, which is usually modeled with a so-called view vector or an eye vector. And the light direction is, of course, can be modeled with another vector, which is then often called the vector L for, obviously, light. Now, when we do a simplified model, we often ignore these distances here, because they do have an influence, but especially when we have light sources that are far away, like if we have a light source that is 200 meters away or 20 meters away or 20 and a half meters away, it doesn't really change very much. Also, if I'm moving like 10 centimeters back and forth, it doesn't really change that much how I perceive a light, which is why in simplified models these are often ignored. Another thing that we always do, and that's not necessarily true for simplified models, in fact it's even more important for more complex models, is that we model these vectors with the unit vectors, because if we have them have a length of 1, it will make the calculation much easier. Good. So if we look into physics, how people perceive light and how the light direction influences how we see light, there is this Lambert's cosine law, which specifies a relationship between the direction at which the light hits an object and how we perceive the color of the object at this particular point. And that cosine law says that the color at which we perceive an object is proportional to the cosine of the angle at which the light hits the object. So if this is the vector pointing towards our light source, so if this is, let's draw it like the sun, which is probably bad because it's not a directed light, but yeah. Let's say this is the light that shines here, and it hits the object at an angle with a normal vector theta L. Then the color at which we perceive this object is proportional to the cosine of that, which, if you remember the scalar product, also means it's proportional to the scalar product. And in fact, if we use unit vectors for n and L, it is directly proportional to the cosine of theta L, because then the length of the unit vectors is 1, so these values in these factors in the scalar product don't add to it, so it is directly proportional to the cosine of theta L, which is of course an advantage, because that means we don't have to calculate this angle. We can just do the arithmetic calculation of the vector of the dot product by and then we get the actual value. Now, if you think about what that means from a physical understanding of how it influences the light, of course, look at the cosine function. You have a maximum value for 0, which means if the light shines directly onto that spot at an angle of 90 degrees with a normal vector, then you get a maximum. And the more you move it away to an angle of 90 degrees, the less brighter the spot becomes, the less strong is the influence of the light that hits the spot here. And of course, we also see if we go down, then the cosine gets negative, which of course makes sense, because it would mean the light source is behind the object that we are looking at, which means it doesn't hit this spot here, unless it's of course a transparent object, in which case we have to do a different treatment anyhow. Or if it's a solid object, we don't see it. So if it is negative, then of course the angle is larger. We know if the scalar product is negative, we know that the light source is behind the object, so it doesn't have an influence on the color at this point. So if we want to express this, we can model it with this equation here, which calculates the color value that we perceive depending on the intensity of the light and how the light hits, or the direction that the light hits the object, by taking the scalar product, which is directly from Lambert's cosine law, which gives us a value that basically scales the influence of the light. And like I said, it's a maximum if the light shines directly onto it, and it is a minimum if it comes from the very extreme side, which kind of makes sense, like if you take a flashlight and put it on a point and then you move it to the side. Of course, if you have it there, then it only slightly touches the spot, but if you have it directly pointed straight at it, you will have the very much brightest spot here. And this is modeled here. Now we see in the equation we added this max of 0 times the scalar product, and that is of course to deal with the case that the scalar product can of course be negative, but that is exactly the point where we don't have an influence of the light source, because if it's behind the object, and that means we just set it to 0 then, because of course if this is negative and 0, then the max will be 0. And then of course when we want to calculate the value, we don't have it proportional, but we need to really explicitly specify the value. And then of course, if you think about it, what we said at the beginning, where does it depend? It depends on the direction of the light, but of course it depends also on the characteristic of the light, like white light, yellow light, and also of course on the color of the surface and how much the surface reflects it. And a very simple way to model this is by just using a constant factor that then illustrates the factor the surface color, and another factor that specifies the light color or the intensity of the light source. So it's basically just a factor that is proportional to the intensity of the light source, and a factor that represents the color of the object and how much it reflects light. And then we take this into account, and then we can take the product of it, and then we have our color at this particular spot. And with that way, we can produce the kind of light that you see here at the left side. And this is called a diffuse light, because it is kind of a light that you have with these typical matte surfaces where all the light is reflected in an equal way. But that is, of course, not true in nature if we have a more polished area, because then we have these bright spots that are much higher, have a much higher reflectance than the spots where we have around it. A typical example would, of course, be a polished bowling ball, where if you have a light, you always have these bright spots that you see here. And this is something that we can model with the so-called Phong reflection, or a variation thereof, which is called the Blind-Phong reflection, which is based on the observation that we say if the angle of the incoming light is the same as the angle that the observer has to the light, to the spot, to the normal vector, then, so if these two vectors are identical, then we have a maximum. And the small, when they move away from each other, then the influence of the light decreases. So this is why when the angles match, we get this bright spot here, and when they don't match, we do not get the bright spot here. And you see here also, this is in contrast to this one, where I have drawn the vector E, the position of the observer, but not considered it anywhere here, because for these matte surfaces, it doesn't matter where I'm standing. So if I'm moving a little bit here, the surface here always stays the same. But if I look, for example, at my watch here, and the silver reflection, which has this bright spot, of course, that bright spot, that moves when I move here and look at it from a different perspective. So this is why this is also dependent on the viewing direction, which is why we have to consider both angles. And if both angles match, if both are identical, then we have a maximum. So we could calculate these two angles, and that is indeed the Phong shading. Now, the Blind-Phong shading is just a simplification of it, or a more efficient way to calculate it. It produces not exactly the same result, but there is not really that much of a difference, which only looks at this vector that is in between the E and the L vector. So it's called H because it stands for halfway vector. And then it compares this vector with respect to the normal vector. And then again, we have the very same situation, that it is we had a maximum when they are in line, and it decreases the more it moves away from it, which is basically the same as comparing these two angles with each other. It's just a more efficient way, and it's more efficient because we can calculate this vector very easily if we have unit vectors. Here is one of the points where it comes really into play, that we have unit vectors, because otherwise we could not calculate it with that equation here. And it is, by the way, a good exercise to make yourself clear why we have this equation based on the image here. Yeah, so if you draw the lengths of the vectors and the relation to them, then you will see that you end up with this equation here. And like I said, it's a good exercise to do that. But you see also here, we can calculate this vector without calculating any angles. And then we can also calculate the scalar product here without calculating the angles, but use it by using the arithmetic way of it and not the cosine definition. And then we can calculate, we have this influence factor here. And then we again need to consider the intensity of the light, and we need to consider the intensity of the object. In this case, it's a different coefficient, because of course we have here this specular reflection. And another thing we see here is, of course, this value P here, which is drawn here, which is the so-called Phong exponent. Now you might wonder, why do we do that? This is just a way to basically modify how big the influence is of this light at this particular spot, or how big we want to make this reflecting spot. It's just a way to model different kinds of reflective surfaces, because if you draw it and you modify the Phong factor, so this is an image from the book, this is for p equals 1, and this is p equals 256, the others are in between. And you see here by increasing the Phong value, we make this bright spot here much smaller, or by decreasing it, we make it much bigger. So we have a way here to create different kind of effects, a different kind of reflections, or different intensity of reflection by just twisting and modifying this one parameter. Good, so we can calculate the light now. We have a way to calculate this glossy reflection. We can calculate a diffuse reflection. But of course, we also have a situation where we have an object that is not directly hit by a light source, but that object might still be visible to us. So for example, if we have an object here in a shadow, it is not directly hit by any light source, but you can still see it, because in nature, of course, light is reflected from everywhere. But since we have, and we could of course calculate that by calculating the reflections of the light when we have an object, but that would then be, of course, not be a simplistic shading model anymore. And one trick to do it is this so-called ambient light, where we basically say we add a basic light color to all objects that we have, to all positions or pixels that we have on a screen. They have a basic ground light, so-called ambient or global light, and that is then always there, and it's always the same, and that's why we just need these two coefficients, the surface and the intensity of this ambient light, to use it. So it's basically just a constant value that we add to all the lights that we have. Good, so we can model the three different kinds of lights now, but of course we want to model them all together. We want to have an image where we have all light sources considered. So what we do is we basically just add them up to get a light, to get the color at a specific point. So we take the ambient light, then we take the diffuse light, and then we take the glossy specular component, which is, if we have these glossy reflections, these reflection spots, then we also add them to our light calculation, and then we have the color calculated with a very simplistic light model, which allows us to already produce quite nice images with very nice light effects. And we can even use those to, we can even extend this by adding more light sources. So this, of course, just considers one light source, but if we have a situation where we have a lamp here, and then of course another lamp here, then we can calculate the ambient light for both light sources, and in this model this just leads then to a sum of the multiple light sources for the ambient light, but also of course for the glossy reflection. Of course, this factor here is not summed up because this is just one time there, because this is just the ambient basic light that we have there, and of course that is the same no matter how many light sources you have there. Good. So this is basically also what you have to implement in the practicals, these different kind of shadings in one of the assignments. Another word on the practicals, there is also an exercise about texture mapping, which is covered in the last lecture before the midterm exam. So there is still then some time to do, enough time left to do it after that lecture. So because that is something that you will not understand immediately without the lecture. But if you already want to start, you can look at the book or the material from last year. I posted the links. I think they're also in the assignment actually. You can already start with that, or you can ask the TAs and they can give you the pointers with it. But this is the part of shading that you can already start. And like I said, I would recommend to start with it very soon. Are there any questions to that part? No? No, I'm not done. Yeah. Just to remember that there will be these two talks and that we will extend the practical sessions. Most likely I will put it online tomorrow when the practical sessions will extend, because the first one is of course also the one that collides with the deadline for the first assignment, so we'll have more TAs there anyhow. Tutorials take place as usual, so like I said, attending one of the talks is not excuse to miss one of the tutorials. Yeah, that's basically it. Are there any questions? No? Then see you in the tutorials or then next week.